peat. The kind of stuff you put on your garden. We're in Somerset, near Glastonbury, in the Somerset Levels. And the Somerset Levels are a large area of peat bog. Nowadays, the peat is being cut and sold for horticultural purposes, but we're interested in the past. The trouble with peat is that it's extremely wet and very difficult to get around on. So that the people who lived here thousands of years ago laid wooden trackways to connect their settlements on the higher ground in the peat bog. Now, one of the advantages of peat from our point of view, the advantage of it being so wet, is that when wood is buried in peat, it doesn't rot away immediately. It gets preserved for a long, long period. This excavation has uncovered part of a wooden trackway which ran between an ancient settlement near the modern village of Westhay behind me and another smaller settlement on higher ground just over here. Now the question is, exactly how old are these remains? We get some idea from looking at how deeply they're buried. Archaeologists can date their finds by, for example, looking at remains of pottery or tools that they find when they're digging. But this is not a very accurate method. And we want to know exactly how old the trackway is. Let's look at a particular piece of wood, like this one. This is the remains of part of a post which stood beside the track. How long has it been standing there? That's the problem that we're going to look at in this program. We've chosen to look at this problem because in solving it, we have to solve a related mathematical problem. The thing that we need is some characteristic property of the wood that we can measure and that we can use to date the wood. Well, to find out about that, we're going to have to leave archaeology for the moment and talk about physics. The usual scientific method of finding the age of a piece of wood like this is called radiocarbon dating. This piece of wood consists largely of the element carbon, but not all carbon atoms are the same. Some of them, a small percentage, are radioactive. And radioactivity is something we can detect with a device like a Geiger counter. Of course, a lot of this radioactivity is coming from stray radiation all around us, but some of these clicks that you can hear come from the radioactive carbon in the wood itself. The relationship between the radioactive carbon in the wood and the wood's age will lead us to talk about exponential functions. But before we get involved in the mathematics, we'll have to take a little time examining the nature of radioactive carbon. The difference between carbon atoms is in the nucleus. The most common type of carbon atom has 6 protons and 6 neutrons, so it's called carbon-12. It's not radioactive, but naturally occurring carbon contains small proportions of slightly different atoms. Some have an extra neutron. They're called carbon-13. They're not radioactive either. But a smaller proportion still have a second extra neutron. They're called carbon-14. And it's the carbon-14 atoms that are the source of the radioactivity. The carbon-14 atom is unstable. It can't hang on to its extra neutrons. It will remain as it is for a while, but eventually one of its neutrons will change into a proton. When this happens, a particle is emitted. It's this emission which is detected by a Geiger counter. The atom we're left with now has 7 protons and 7 neutrons. It's nitrogen, and it's not radioactive. We say that the carbon-14 atom has decayed to nitrogen. Now, in our lump of wood as a whole, there are millions of atoms. A small proportion of them, but still a very large number, are carbon-14 atoms. These carbon-14 atoms are decaying away all the time. Their numbers are getting fewer and fewer. It's this gradual decrease in the amount of carbon-14 in the wood that provides us with a physical process which we can use to determine age. Well, that's the principle of radiocarbon dating. When this piece of wood was new, it had a certain amount of carbon-14 in it. As time has passed, that carbon-14 has been getting less and less. So the amount of carbon-14 that still remains in this wood provides a guide to its age. The less carbon-14, the older the wood must be. But before we can actually use carbon-14 as a measure of age, we have to find out exactly how carbon-14 decay is related to time.
This is the point we get our first taste of mathematics. The problem with carbon-14 is that the length of time before any individual atom decays is unpredictable. In that respect, it's a bit like this die. It has 5 red faces and 1 white face. And asking how long a carbon-14 atom will live is like asking how many times I must throw this die before it turns up with a white face. It might happen on the first throw, the second throw, or it might not happen for 100 throws. Fortunately, we're not interested in the behavior of individual atoms. We want to look at the overall behavior of a large number. Now, I've got about 17 white dice here, and if I think of them as representing decays, I can build up a graph of the number of decays like this. And then I can work out what happens as time goes on by throwing the ones which did not decay again, like this. Pick out the decayed ones again and build up the graph. And so on. We continue repeating this procedure. After each throw, we take out the white dice and stack them on the graph, and we then throw the remaining dice. In that way, we build up a graph of the number of white dice on each throw. Well, that gives us a graph of the white dice, or decays, but we're interested in the number remaining red after each throw. Now, I've kept a record of the throws on this other graph. At the start, we had 100 red dice. After the first throw, there were 83 red dice and 17 white. So we took the 17 out and threw these 83. After this throw, there were 69 red dice, and so on. Now, without actually doing the experiment, we should have predicted this sort of outcome. Remember, when we threw the dice, about 1/6 landed white, so about 5/6 remained red. So if we start with 100 dice, after the first throw, we expect about 100 times 5/6 to remain red. We then took these dice and threw them again, and once more we'd expect about 1/6 to be white and 5/6 to be red. So this next figure should be 100 times 5/6, that's the number we threw, times 5/6 again, or 100 times 5/6 squared, and so on. 100 times 5/6 cubed, etc. In general, after x throws, we'd expect about 100 times 5/6 to the x, red dice remaining. In fact, if we plot the graph of 100 times 5/6 to the x, we can see it's a pretty good fit to the data. Exactly the same sort of behavior occurs in carbon-14 decay, but instead of 1/6 decaying each time, only about 1 in 8,000 of the carbon-14 atoms decay, and that's in a whole year. So whatever amount of carbon-14 we start with, after 1 year, only 1/8,000th of it has decayed. So there's still 7,999 8,000ths left. And after X years, there'll be 799 over 8,000 to the power X left. So the proportion of carbon-14 remaining after X years is 7,999 over 8,000 to the X. This is our mathematical statement for carbon-14 decay. And of course, you've noticed that it's an exponential function. Now, to plot a graph of this function by hand would be extremely tedious, so we'll use a computer to plot some points. We start when x equals 0. Anything to the power 0 is 1. That's our original amount of carbon-14. After 1 year, we have 7,999 over 8,000, which is pretty close to 1. After 2 years, we have 7,999 over 8,000 squared, still pretty close to 1. And after 3 years, we cube it. We'll plot points for powers up to 10. There's no noticeable decrease in 10 years. Perhaps we'll see more if we squeeze up the x-axis. That takes us for x from 0 to 100. There's still not much sign of a decrease. Let's squeeze the x-axis up yet again. Now at 1,000 years, we can see a small decrease. Let's squeeze up one more time. With x values up to 10,000 years, we get a graph that's more recognizable. The graph of carbon-14 decay looks much like the exponential graphs you've plotted earlier in the unit. The difference is in the scale along the x-axis. A way of distinguishing this particular graph and timescale uses the idea of half-life. Now, the half-life is simply the time taken for half the substance to decay away. In this case, just over 5,000 years. A larger half-life means a larger timescale. Now, that completes our mathematical model for carbon-14 decay. We have a mathematical function relating the amount of carbon-14 to time. The next step is to use this model to actually date our sample of wood.
Where this piece of wood actually grew in a tree, its carbon contained a certain amount of carbon-14. Since then, that carbon-14 has slowly been decaying away. So if we knew what proportion of the original carbon-14 was still in the wood, we would know where we were on this axis, and we could read off the age. Well, to find that out, I need two things. Firstly, how much carbon-14 was there originally? And secondly, how much there is now? But how on earth can I find out how much carbon-14 there was in this wood when it was new, which may have been thousands of years ago? Well, for that, we need to know where carbon-14 comes from in the first place. Cosmic rays in the upper atmosphere convert nitrogen atoms to carbon-14. This carbon-14 mixes uniformly with the rest of the carbon in the atmosphere in the form of carbon dioxide. It's the carbon dioxide which is absorbed into growing plants and trees. So the proportion of carbon-14 in the new wood in the tree matches the carbon-14 in the atmosphere. Once in the wood, however, the carbon-14 is trapped. Outside influences can't affect the carbon-14 in the wood. All that can happen to it is that as time passes, it slowly changes back to nitrogen. These processes of carbon-14 creation in the upper atmosphere and carbon-14 decay just balance each other. So the proportion of carbon-14 in the atmosphere doesn't vary. It's constant. And we believe has been constant for many thousands of years. So to answer the question, how much carbon-14 was there in this piece of wood when it was new, all I need is a new piece of wood. So to find out how much carbon-14 was in this piece when it was new, I just need to look at this new piece. Well, that leads us to the second problem. How do we measure the amount of carbon-14? We can't measure the amount of carbon-14 directly, but we can measure the radioactivity, using a Geiger counter, for instance. And the greater the radioactivity, the greater the amount of carbon-14. Well, we can see that by looking at the dice again. If we throw a small number of dice, we get about a 6 of them turning up white. A larger number gives more white dice. Now, we can't measure radioactivity in a room like this, with stray radiation coming in. We need special screened, protected counters. A special laboratory at Harwell can accurately measure the amount of radioactive carbon. Firstly, the wood must be burnt. The carbon is drawn off as carbon dioxide. After many purifying processes, there remains a small sample of benzene made entirely from the carbon in the wood. Exactly 5 grams is drawn off. A liquid scintillator is added, so the carbon-14 decays are detected as tiny flashes of light. Deep inside this machine, these tiny flashes are detected and counted. The time taken for 20,000 decays is automatically recorded. The same treatment is applied to a sample of new wood. An identical quantity of carbon must be used for the decay measurement. Comparing the time taken for 20,000 decays in this sample gives a measurement of the carbon-14 content. The outcome of the Harwell experiment was that the sample from this old piece of wood had only 0.6 of the carbon-14 of the sample from this new piece. So now I can put that in the mathematical model. And our original practical problem of dating a piece of wood has boiled down to solving a mathematical problem. Well, a rough way to get an answer is to look at the graph. We get about 4,000. Remember what that means in terms of our original problem. This piece of wood is about 4,000 years old. Well, 4,000 years old, that's a bit rough and ready. Can you think of a technique that will give a better solution to the equation? There's no algebraic way that we can solve it. It'll have to be a numerical method. Well, I'm going to use the slow but sure method of bisection. And to save myself a lot of writing, I set up my trusty microcomputer to do it for me. I started with quite a wide interval, and I let the program run until, at this point, it stopped, and I know that my solution lies somewhere in this interval. That interval is less than 20 years. And really, that's as accurately as I need the answer, considering the limitations of the experimental methods and what I need the answer for.
20 years might be all right for an archaeologist, but I'm a mathematician, and when I'm given an equation to solve, I want to solve it as accurately as possible. So let's forget about our dating problem for the moment and concentrate just on solving this equation. Well, we've started using bisection, so let's carry on. Now, there are a number of features about this. First of all, halves and quarters are beginning to appear. Well, that's fine, because I know how to find a to the x for x a rational number. But we're also producing a nest, and this could be nesting to an irrational number, and I don't know a to the x for irrational values of x. But the bisection method works quite successfully, and I think it gives us a clue as to how we can define a to the x for x an irrational number. We have a graph for the exponential function, but we've only plotted points for rational values of x, and then drawn a curve through them. For an irrational number r, we don't properly know how to work out something to the power r. What we do know about are rational numbers. We can calculate a to the r for r rational. So we choose a pair of rational numbers, one each side of r. Now we assume that all numbers in this interval get mapped into another interval. Now a way of getting to grips with an irrational number is via a nest. We have an infinite sequence of intervals that close in on r. Each interval has a rational number at each end, and we know how to calculate exponentials with rational powers. And once again, we assume that an interval on the x-axis gets mapped to an interval on the y-axis. Similarly, for the next interval in the nest, that gives a nest on the y-axis. This nest will home in to a single number, and we can define a to the power r as this number. So that means that we now have a way of defining a to the power r for any number r, rational or irrational. I can now say something more about exponential functions. I can define the domain to be the whole of r. And functions with domain r are a lot easier to deal with. In this case, what we're really doing is finding an inverse. And we have a procedure for doing inverses. We flip the graph. And in the process box, we first have to put in the image set. And now we flip the box. We're now at the last crucial stage, putting a to the x maps to x in the form x maps to something. Now we define the inverse function as x maps to log to base a of x. So our original problem now becomes taking point 6 and finding the log of 0.6. And logs are something you have on your calculator.
Well, by using inverses, we've managed to change this equation, where a is this number, into this form. And now it looks easy for me to get x by using my calculator, which of course has a log button. So what I'll do, turn the calculator on, enter 0.6, and then I'm going to use its logarithm. Wait a minute, there's a snag here, isn't there? How am I going to enter the base a of the log?
The log button on the calculator relates to a base of 10, and log to the base 10 is the inverse of 10 to the x. Now we've noted already that all exponential decay functions are a similar shape. It's just the time scale that differs. Now another way of saying the same thing is that any exponential can be got from any other by a suitable x scaling. Now we can get this exponential by an x scaling of 10 to the x. So for the inverses, this inverse must be a y scaling of log to base 10 of x. And that tells us that log to base a of x is some multiple, k, of log to base 10 of x. Now by methods you'll see later on in the unit, k in this case turns out to be about minus 18,420.
So we know that log to the base a is a scaled version of log to the base 10. And that means that we can find log to the base a of 0.6 by finding log to the base 10 and multiplying by a suitable constant. And in fact, in this case, the constant turns out to be this number. And you'll find out why that's so later in the unit. Okay, so here goes. Let's do this calculation. Put in 0.6, and then I take its log to base 10, and then I have to multiply by this number. Well, I actually had that stored away in the memory. That gives me that. And so the solution to our mathematical problem is 4,086 plus a bit. And so we know the age of that wood sample, well, plus or minus 50 years, because carbon dating isn't perfectly accurate.